Welcome back to the Deep Dive, where we streamline complex research into insights you can use. Right now, there's this huge global push for biodiversity conservation.
Absolutely. We're all talking about the new global biodiversity framework.
And when you want to measure how an environment is doing, birds are. Well, you could argue they're the best indicators we have, especially in our urban parks.
That's right. But for a long time, researchers were operating with, a flat two-dimensional map when they studied urban ecology.
They were just looking at horizontal factors.
Exactly. How large is the park? What's its perimeter? How do the green patches connect? Just simple area metrics.
The basic footprint.
Yeah. But a modern city is intensely three-dimensional. You've got soaring high-rises. You have complex, multi-layered trees and shrubs.
So if you ignore that vertical structure,
Yeah.
you're missing a huge piece of the puzzle.
You're missing the critical elements that shape where birds actually live and feed and nest. So our mission today is to dig into what happens when you finally integrate both the horizontal and the vertical.
And our case study for this is a really fascinating choice. Harbin in northeastern China. It's a high-latitude, very cold city, which already presents its own unique challenges.
And Harbin is so strategically important, it sits directly on the East Asian-Australasian flyway.
So its parks are basically crucial stopover points for migratory birds.
Absolutely crucial for huge populations. So understanding how Harbin manages its green space, well, it has implications far beyond just the city limits.
The foundation for this deep dive is pretty robust. It's relying on a massive amount of citizen science data.
It is. The China Bird Report, over 4 years, that's 141 species and over 25,000 individual bird records. It's a really substantial data set.
And the analysis method is what really stands out here. They use these advanced nonlinear machine learning models.
It's like random forest, yeah. But crucially, they weren't interested in the black box problem.
Meaning they didn't just want a prediction. They wanted to know why the prediction was made.
Precisely. They used a technique called SHE. It stands for Shapley Additive Explanations, to kind of peel back the layers and understand how every single feature was contributing.
So let's find those exact sweet spots.
The thresholds, the points where something good flips over and becomes harmful.
Okay, let's unpack those core findings then. Using that random forest model, what were the most important drivers for overall bird richness in Harbin?
Well, this is the first surprise. The most important drivers were actually factors related to disturbance.
Disturbance.
Yeah, specifically how connected the built-up land is and the total coverage of commercial buildings. It immediately shows that you can't just focus on making parks bigger, you have to manage the city around them.
And because of that SHEP analysis, we can get into the specific numbers. So let's talk about commercial buildings. It seems like a little bit of commercial coverage can actually help.
It can, perhaps by creating complex edges, but there is a very specific cliff. Once commercial building coverage exceeds 22,000 square meters in an area, its contribution to bird richness just tanks. It becomes negative.
So that's the point where all the noise, the light pollution, the traffic, it just overwhelms any benefit.
Exactly. It's a clear tipping point.
Now, this next finding is, it's completely counterintuitive for any city planner. Green space proportion. You'd assume more green is always better.
You would think so. But the data here suggests otherwise. Green space area only contributed positively when it was below about 8% of the total area.
Wait, below 8%?
Larger proportions either contributed negatively or basically did nothing at all.
So if you have a massive park, it could actually be worse than having a few smaller green patches. Why would that be?
Well, the thinking is that in Harbin's really dense city center, these huge swaths of green space are often, they're uniform. Think big manicured lawns or rows of identical street trees.
So it's high percentage green, but low habitat variety.
Exactly. It's a process we call biotic homogenization. It filters out the specialist birds because there just aren't enough different niches for them, even though it looks very green on a map.
Wow. That is a huge philosophical shift. It's not about quantity. It's about the quality and the complexity inside the park.
And we see that same issue with complexity when we look at the vertical structure of the trees.
Okay.
Tall trees, so anything over 10 meters, they actually started contributing negatively to richness once their cover exceeded 12,000 square meters.
So too much canopy cover is a bad thing. How does that work?
A dense, uniform canopy layer. It basically acts like a roof. It blocks sunlight from reaching the understory.
So you lose all the shrubs and the lower vegetation layers.
You white them out. And that's essential shelter, it's food, it's nesting sites for so many species. You've collapsed the vertical structure down to just one layer.
Okay, and finally on this, what about water? We know it's vital, but the data show that it only really helped if the largest patch of water was, what was it, bigger than about 10% of the area.
Yeah, the water patches have to be substantial. Little ornamental ponds are just too vulnerable to pollution and disturbance to be reliable habitats. You need that minimum size for them to really function as ecological anchors.
So these nonlinear insights are really the foundation for everything else.
They are.
Okay, so let's shift our focus a bit. We talked about overall bird numbers, but what about the composition? You mentioned they did a redundancy analysis in RDA to see how specific groups of birds respond.
This is so crucial because you can accidentally maximize richness by just attracting a ton of generalists, like sparrows and pigeons, at the expense of specialists, and the RBA clearly pulled the groups apart.
Let's start with the water birds, like the black-headed gull, and the generalist birds, like the tree sparrows. What did they like?
So these two groups actually clustered together. They showed really similar preferences for mixed, messy, edge-heavy habitats.
Right.
They liked large water patches, lots of tall vegetation, and just high land use heterogeneity. And they were mostly found along the Hangzhou River basin.
In that location where the river meets the city,
Yeah.
what does that tell us about what's helping them thrive?
It's a textbook example of edge effects. All that complexity created by the built-up boundaries right next to the river and the wetlands. It provides all these different microclimates and extra resources. They're just very adaptable to those human-made edges.
Okay, now for the forest birds. Things like the azure-winged magpie. Their response was the one I found truly paradoxical.
It is. They were, on the one hand, associated with what you'd expect. Large, continuous, high-quality green spaces.
Right.
But they were also positively associated with indicators of intense urban disturbance. We're talking high building density and even the average building height.
So why are these forest specialists seemingly okay with, or even preferring, areas surrounded by high-rises?
Well, this is where you start to see the hidden cost of their survival. Their tolerance for fragmentation and tall structures allows them to colonize those little embedded green spaces right in the heart of the city.
They're exploiting the little pockets of nature that are left over.
They are, but, and this is a big but, it only allows a certain type of forest bird to succeed.
So what's the ecological trap here? What's the downside?
You're touching on what's called the filter effect. The city acts as this really strict filter, and it only lets through the species that can handle all that disturbance. And while it's great that those species survive, the source warns that it leads to lower functional diversity overall.
And that leads back to that homogenization idea.
It accelerates it. The local ecosystem becomes dominated by just a handful of the same super tolerant species you find in cities everywhere.
So we've diagnosed the problem, we found the sweet spots. Let's get into the practical advice, the 3D planning prescription based on all these numbers.
Right. And the recommendations are really specific, which is great. They give planners concrete goals to aim for. Let's start with the horizontal stuff, managing the city around the parks.
What should planners do with that built-up land?
They should aim for moderate connectivity, but low aggregation. Keep it below 98% per 0.7 square kilometers. And they actually need to embrace a certain level of fragmentation.
More fragmentation.
Intermediate fragmentation, yeah. Something like more than 80 built-up patches per 100 hectares. This creates those complex boundaries we talked about. And they also suggest making patches more square shape to minimize the intensity of the artificial edge.
You're basically designing the city to be a better neighbor to nature. What about inside the green space itself to fight that homogenization problem?
We have to move away from sterile parks. The advice is to limit that single-layer, heavily managed green space, so the big lawns, to less than that 8% threshold we discussed earlier.
The goal is variety inside the park.
Structural variety, exactly. And for the blue infrastructure, the water and wetlands, they have to be numerous and they have to be big enough to matter.
So planners should be aiming for, what, more than 4 patches per 100 hectares?
At least, with the large patches covering more than 10% of the area. And this is key. They have to be connected into a functioning wetland network. They need to be stepping stones for migratory birds trying to navigate the city.
Okay, finally, let's address the vertical dimension. How do you manage building height and tree height?
Building control is absolutely key. So, first, reiterate that limit on commercial buildings. Keep the coverage below 22,000 square meters. That's to manage the noise and light. And then controlling the overall average building height is also critical for reducing bird collision risks.
And for the trees. to avoid that simplified canopy problem.
The goal here is a complex, multi-layered vertical structure. That means you have to intentionally increase vegetation cover at both ends of the spectrum.
Both ends.
Yep. More vegetation that's tall, so greater than 147 centimeters, and also more vegetation that's short, so less than 50 centimeters. That creates real niches.
And then there's that hard limit on the tallest trees.
Don't forget that one. Keep the total cover of trees over 10 meters tall below 12,000 square meters. That's the only way to guarantee enough light gets down to the understory.
We've really gone from these big global conservation goals all the way down to specific, measurable standards for a city's vertical landscape. The conclusion is pretty clear. You can't understand urban ecology just by looking at a map.
Not anymore. Integrating these 3D features is fundamental if you want to design parks that actually help a wide range of birds, not just the usual suspects.
So this research really provides a kind of design roadmap for cities like Harbin to plug into those global biodiversity efforts.
It moves park planning into the realm of quantitative spatial ecology. It's a huge step forward.
All right, here's a final thought for you to take away. Even with this incredible amount of data, 25,000 bird records, and these sophisticated tools like random forest and SHAP, the source material notes that the overall explanatory power of the models, the R-squared value, was still relatively low.
That's actually a pretty common finding in urban ecology. So why should you care? It means that even after you identify 17 critical 3D environmental variables, the system still resists a complete explanation. It just reinforces that these urban ecological systems are, well, they're inherently complex and uncertain.
So you have to ask yourself, what other hidden variables might be shaping these ecosystems? Maybe it's microclimates or specific human interactions, or maybe it's insect data that they just couldn't capture. The point is, the quest for complete knowledge is never really finished.
A good reminder that every deep dive just opens the door to the next mystery.
Absolutely. Thank you so much for guiding us through this three-dimensional world today.
My pleasure.
And thank you for joining us on the Deep Dive. We'll see you next time.